All right, welcome to our last part of this chapter, and this is probably going to be a very interesting part for you because we're going to talk about where this energy is coming from. So remember, our first law of thermodynamics is the energy of the universe is constant, but in a nuclear event, we're actually generating energy. So gamma rays, that isn't coming from a chemical reaction. And so that energy is actually being driven by something called a mass defect. And so we're going to talk about that today. We're also going to talk about fusion and fission. So we're going to understand the difference between fission and fusion, the atomic bomb, the H bomb, the difference between these. In our Zoom meetings, we're going to do some calculations involving mass defect and nuclear binding energy. And then we're also going to talk a little bit about nuclear transmutation. So the first thing I want to talk about is the difference between fission and fusion. And fission came about first. And fission was really this brainchild of an Italian scientist named Enrico Fermi in the 1930s. And what he thought is, I wonder if I can take an element, bombard it with a neutron, allow the nucleus to absorb that neutron, make a whole brand new element. That brand new element will come from the neutron converting into a proton and undergoing a type of beta decay and emitting a beta particle. And so he took uranium-238, he bombarded it with a neutron, and what he found is he could measure the beta emission coming off. So he knew that he had caused some sort of event to happen in the nucleus, but he was never able to measure this newly synthesized product. He didn't know if it was there or not. There wasn't a whole lot of evidence for him to be able to determine that. That idea kind of got shelved for a couple of years, and then in 1939, there was 3 German scientists who came and kind of resurrected this idea. Instead of taking uranium-238, they took uranium-235, a different isotope of uranium, and they bombarded it with a neutron. And what they saw is not just one particle, but they saw 2 lighter particles coming out of that, as well as 3 neutrons and a ton of energy. And then fission was born. So fission is taking a heavier particle and bombarding that with a neutron. As that particle absorbs that neutron into the nucleus, it makes it unstable, and then it actually splits into 2 smaller, lighter particles. And then it emits 3 neutrons and then a bunch of energy. And so this type of process is called self-amplifying, and that's where the power of this idea of fission comes from, because if it takes 1 neutron to start that process and the result of that process is 3 neutrons, now you have something where you can self-amplify. If I have more uranium-235 nearby, as that first one undergoes fission, then it's going to create 3 neutrons, which are going to bombard 3 other uranium molecules, which are going to undergo fission, and each of those 3 are going to produce 3 neutrons, and as you go. So that's amplification of this nuclear process. In order for this self-amplification to happen, you need a critical mass. So you can't just have 10 uraniums. You need a certain amount of uranium that reaches that critical mass, and then you can get this self-amplification to happen. When the Manhattan Project started, and if you haven't read too much about this, it's super interesting. So it was the US's goal to build an atomic bomb first before Germany. And at the time, we knew that these 3 German scientists in late 1939 had proven that fission worked, but it wasn't feasible to do it on a large scale. No one had been able to set up that experiment so that it would self-amplify. It was kind of hypothesized at the time that you could have self-amplification happening, but nobody really knew for sure. Hitler didn't put too much stock into it, and so the German scientists that were working on the project didn't get a lot of the support. The backing of the country wasn't really behind it, and so they kind of fell behind on this race, but the Americans kind of jumped on board, and that's when we formed the Manhattan Project. There was land kind of all over the United States that was being bought up to be places where they could build reactors to synthesize uranium-235. And then they started building this thing in Chicago called the Chicago Pile. And this was in the early 1940s. And this was the first self-sustaining nuclear reaction was successful in the middle of Chicago, on the University of Chicago. They basically took this large pile of natural uranium with graphite blocks that were sandwiched in it, and they actually had 4.9 tons of uranium and 45,000 pure graphite blocks. So all this had to be manufactured and then transported to Chicago, and they put it under the stands of Stagg Field. Today, this would never, ever happen. It's now demolished. This area is now demolished, and there's like a Chicago landmark there. So if you're ever in Chicago, it might be kind of cool to go see it. And so it's kind of a really cool story if you ever have some time and want to get into it. But basically, the scientists there, they had done this test, and it's started to work, and then the fail-safe mechanism came on and the graphite rods were dropped down, and it basically stopped the self-amplification. And then the scientists were like, well, let's just go to lunch. And then they came back after lunch and tried it again and adjusted the point at which those graphite rods would drop down, and then they had the self-amplification. So that was the first demonstration that you could actually have this ability to build a weapon out of uranium and allow it to self-amplify, and so you could have it's a massive amount of energy that would be released from it. And so after that experiment in Chicago, it took 4 years before they were to do the first test of the atomic bomb, and they did that obviously in New Mexico. And the force of that test bomb was the equivalent of 18,000 tons of dynamite, just to give you an idea of the amount of energy that comes out of fission reactions. And this is obviously the self-amplification chain here. This can happen really, really quickly. And this is obviously what it looks like. So this is the atomic bomb. And this idea of fission was harnessed post this to develop nuclear reactors so that we could harness this amount of energy into electrical energy. And so it's the same idea where I have these control rods are made out of graphite. My reactor rods and my fuel rods are made out of uranium-235. And so I allow the reaction to start and bombard with a neutron. Then I start that self-amplification. I can control the speed of this reaction by moving these graphite rods, these control rods, up and down through the fuel rods. And so if I wanted to stop it completely, I would just move those graphite rods all the way down. Obviously, because this generates a whole lot of energy, it also generates a lot of heat. And so in order to dissipate that heat, a lot of these nuclear reactors are put on bodies of water so that they can run water through. That water can dissipate by absorbing the heat from the reactor and turning into steam, and then the steam is released back out. And so that's how they cool these reactors. It used to be, and I don't know what the current stats are now, but it used to be about 20% of the electricity that we were using in the United States were coming from nuclear power. Obviously, the downfall of this is that there's a lot of radioactive waste that comes from this, and the storage of that radioactive waste, and also because you're generating a lot of heat, there can be overheating happen. Some of the radioactive waste that's generated is strontium-90, and its half-life is 600 years. Plutonium is the other, plutonium-239 is the other waste of fission with uranium-235, and its half-life is 200,000 years. So this plutonium-239 that we're generating as a byproduct of nuclear reactors is never going to go away. So where does all this power come from? It comes from this thing called mass defect. So during nuclear fission, some of the mass of the nucleus is converted into energy. For each mole of uranium-235 that undergoes fission, it produces 1.7 times 10 to the 13th joules of energy. So that's where that enormous amount of energy is coming from. It's a very exothermic reaction. And it comes from this mass defect. This nuclear binding energy is the amount of energy that is required to break apart the nucleus into its components. And so if we look at mass defect, if I look at fission, fission's with uranium-235. I'm going to bombard that with a neutron. I'm going to undergo a nuclear reaction. I'm going to emit these two lighter weight particles, 3 neutrons, and a ton of energy. Now, if I were to add up the atomic mass unit, because I know the mass of a neutron, I know the mass of a proton, I could add these up. I know the mass of this isotope here. So my atomic mass unit of this isotope, I'm going to add that to the mass of one neutron, and then I'm going to compare it to the AMU of this isotope plus the atomic mass unit of this isotope, so how much these two isotopes weigh, plus 3 times the mass of a neutron. And these should equal each other. The law of mass conservation says that these two should equal each other. But what I see is that they don't. This is 235.04392. This is 1.00866 AMU. So I'm going to add those two together. That's going to give me this value here. This is 139.910.581 plus 92.93.1130 plus 3 times 1.00866 AMU. When I add these together, what I get is 235, so close, but not the same. So there's a difference here. These do not equal each other. So there's a difference in mass. After fission, it's lost. So there's lost mass here. We call that the mass defect. So that mass that was lost has been turned into energy. So that mass has been converted into energy. Under this equation here, E equal mc squared, E is my energy, obviously. This is Einstein's famous equation. We're going to apply it here. This is my mass that's lost, and this is my speed of light. So I can calculate the energy based on, if I know my mass defect, how much mass was lost, I could plug it into this equation. The energy that's going to be produced, this energy, I'm going to call this the nuclear binding energy. That's the energy I'm going to get out. It's also the amount of energy that I need to break apart a nucleus. We're going to do some of these problems in our Zoom meeting, but just to go over what these units might look like. So I want to measure, and I'm going to get away from joules and kilojoules. Nuclear physicists use something called an eVolt, EV, or a mega eVolt, an MeV. And 1 MeV, 1 megavolt, equals 1.602 times 10 to the minus 13 joules. And this is per nucleus. So not per mole anymore, per nucleus. 1 AMU equals 931.5 mega electron volts. So if I know my mass defect in AMUs, I can get to mega electron volts, and from there I can get to joules per nucleus. All right, so that's fission. Fusion is different. So fission, I'm breaking apart. I'm taking something, a really heavy particle, I'm bombarding it with a neutron and breaking it into lighter particles. Fusion is the complete opposite. Fission, I'm splitting a large, heavy nucleus into lighter particles, 2 or more. In fusion, I'm combining 2 light into a heavier one. So this one I'm splitting, this one I'm combining. So that's the difference between fission and fusion. This is the atomic bomb using uranium-235. This is the H-bomb using hydrogen. This is 1,000 times more explosive than the atomic bomb. But the one thing is I need extremely high temperatures for it to happen. More temperature than I can generate just by heating. And so in order to develop a fusion bomb, one of the things that they had to overcome was, how do you supply this extremely high temperature in order for fusion to happen? And the fusion bomb looks like this. I have an isotope of hydrogen, hydrogen 2. I'm going to combine that with hydrogen 3, and I'm going to form helium. So remember, this is an alpha particle, and I'm going to emit a neutron. So that's my fusion. I'm taking two lighter particles, I'm combining them into a heavier particle. So in order for this to happen, we couple this. So in the hydrogen bomb, this couples a small fission reaction to generate the temperatures needed for fusion to happen. So the hydrogen bomb actually combines both of these together. I have a small fission event that happens that generates enough energy and enough temperature for my fusion reaction to happen, which generates a whole lot more energy than my fission. Because I need such a high, I have to put in so much energy to get this fusion to happen, it's not really viable in terms of a source of energy. It makes a great bomb, but it's not very good for a way to create energy. So this is called the deuterium-tritium fusion reaction because tritium is our name for the isotope hydrogen 3 and deuterium is our name for hydrogen 2. So this is the fusion reaction that happens. This is really nice because you'll notice that the byproduct of this is a lot cleaner than fission because I'm just producing helium and a neutron and a whole bunch of energy. So I don't have all these radioactive byproducts that I have to worry about that are a product of fission. Okay, so let's talk about the effects of radiation. What's happening when you're exposed to radiation? Obviously, it is not good for you. We have increased cancer risk, even if you have a low dose over time. Obviously, if you're exposed to a higher dose, that can speed up this process. And if you have an acute radiation damage, you can have sort of organ breakdown and not survive. Some genetic defects can happen over time. So if you have a high radiation exposure, then your reproductive cells start to cause problems. And we haven't seen this in humans, but we've seen this is in animals that are around where they had the meltdown of the reactor in Japan. We've seen some of these genetic defects start to happen in the animals that are in that area. Measuring exposure is obviously really important. So these are some of the units that you can have exposure measurements in. So Curie, Gray, or Rad, and then REM as well. Like I said, we're exposed to natural radiation daily, but this is just an idea of what some of that natural radiation is. So radon gas is a big problem. It comes up from the ground, and we're exposed to just on average about 200 millirems per year. A 5-hour plane ride, you're exposed to 2.5 millirems per trip. Cosmic radiation from outer space is coming in through our atmosphere. Terrestrial radiation, natural radionuclides that are in our body. So all of this is sort of natural radiation. Diagnostic metal procedures, just to put this into perspective, if you were to get a chest x-ray, that's 8 millirems. Dental x-rays are about 30 to 80. A mammogram is about 140. Consumer products, building materials have natural sources of radioactivity in them, and so you're going to get a small amount of radiation that's coming from building materials. Watches, tobacco products, obviously tobacco is bad for many reasons, but it also, look at this, 16,000 millirems per year. Some other things, so the effects of radiation exposure, so your approximate dose, so this is in rems, not millirems, 20 to 100, you're going to decrease your white blood cell count, so that's going to increase your risk of infection and your ability to fight off viruses and bacteria, and also increases your cancer risk. 100 to 400 rems, you're going to start to have radiation sickness, vomiting, diarrhea, skin lesions. Over 500 rems is death, often within 2 months. Over 1,000 rems, you die within 2 weeks. And 2,000 rems, you're going to die within hours. And this is not going to be a pleasant death either. So radiation is no joke. We use it in medical applications. All right, so we're going to stop here, and this will end this chapter. And I will see you in our Zoom meetings.